Morning, everyone. Today is day 28 of Math 133, so only a couple days left. We are going to work on the Chapter 11 review today. Um, the Chapter 11 review starts on page 563, and there's no lecture notes. This will be uh, the last of our material. So the final exam covers chapters 1 through 11. So today we're wrapping up chapter 11, and then you'll be experts in statistics. Uh, so page 563 in your course pack. Next week is the final exam. Make sure that uh, you have set aside that time uh, for taking the exam. If you're going to be taking it with me on Zoom, it's going to be on December 11th, and we're going to be starting at 9 a.m. and going until noon. Okay. So you have 3 hours to do it. If you're taking it in the evening, we're going to be starting at 6 p.m. and we'll go until 9 p.m. Okay. So again, the final exam is 12 pages, so it's a little bit longer than the midterm. And again, if you felt that you were short on time for the midterm, you want to consider taking it at the testing center. The testing center, you can take it next week, Tuesday, Wednesday, Thursday, or Friday. If you're going to take it Friday, December 12th, you're going to want to make sure you set up an appointment because their hours are a little more limited. I believe they're open 10 to 2. I have to check that. But that should still be enough time for you to do the exam. Um, I'll be sending out a link to a survey just to find out where everyone's plans are, if you're taking it with me or if you're taking it at the testing center, just so I know how many copies to send out. It's okay if you change your mind, okay? But anyway, uh, today, though, we're working on the Chapter 11 review, and you're going to want to click on the link in Canvas for the Chapter 11 review because there is some StatCrunch info that might help out. So if you click on where it says this link, that'll take you to this data set that has all the StatCrunch links for all of our different worksheets. And down here for the Chapter 11 review, we'll click on that StatCrunch. So it's not a lot, and I'll drop this in the chat for you. So honestly, if you needed to type these numbers into StatCrunch, it's not going to take you that long. But we can save ourselves a little bit of time by using that link. Okay. All right. But we're going to start here on page 563. Okay. So I'll give you some hints before we dive into actually finishing the worksheet. So to start with, um, this one's going to be on page 261 at the bottom. Okay. So in 2024, 40% of adults in Michigan, 38% of adults in Wisconsin identified as Republican. You want to conduct a study to find if the difference in these percentages have changed, how many adults and how many from Michigan and how many from Wisconsin do you need to sample to correctly gauge the difference with 95% confidence within a 3.2% margin of error. So bottom of page 261. So this is how to calculate the sample size when you have two different populations. And in this case, we have two populations. One is Michigan, one is Wisconsin. Okay. So you'll want to write out the formula. So just write out, this whole thing here. Okay. Now, do we have a prior estimate? We do. Okay. So these are the prior estimates here. So you'll write out the formula and then substitute in those numbers. Okay. And then your result. And make sure with our result, we're going to round up and you're going to want to list out both uh, states. Okay. All right. Question two, how many adults in Michigan and Wisconsin must you sample to correctly gauge the difference in the percentage of residents that believe in astrology with 99% confidence within a 2.4% margin of error? So this one's very similar to the previous one. Uh, Formula, we need to substitute, and we ran out a result. Okay. Um, so these are two different questions, by the way. This one here, they gave us in 2024, it was these percents. So we have a prior estimate. Um, this one, though, they want to know what percent of residents believe in astrology, and they don't give us any prior estimate. I don't know if you have a guess, you know, but these two questions are not related. So you can't just say like, oh, well, most Republicans believe in astrology. So you can't go with that. Okay. Um, so we're with question number two, we're going to use no prior estimate. Okay. All right. Um, all right. A researcher carried out two-tailed tests. Which of these studies is associated with the smallest p-value? So remember that on your normal curve, the farther you are away from zero, the more you're going to shade on your curve. Okay. If you're looking at something that's very close to zero, like this is 0.5, you're going to shade quite a lot of your normal curve. Okay. So you're going to have a very large p-value if your number is close to zero. So, and it doesn't matter whether it's negative zero point 0.5 or positive zero point 0.5. So when you're looking for a small p-value, you need a number that's very far away from zero. Okay. Regardless of whether it's positive or negative. Okay. Um, Question four, circle true or false after each statement. Explain why if it is false. Type 1 errors are always worse than type 2 errors. Type 1 is always the worst. Okay. And we already know that that is false. Yes. Talked about that before, where sometimes type 1 is a major problem. But we saw in chapter 10 that no, sometimes type 2 is much worse. And how do you know what's worse? Well, it depends on context. Okay. All right. It depends on what kind of situation we are talking about. Okay. So, uh, yeah. um, I was trying to find an example. That's okay. We'll just move. We'll move on. Okay. Next, we're going to move on to page 564. All right. A new post-surgical treatment for common surgery is being compared with the standard treatment. So we have two different samples, okay? We have the standard and we have the new one, okay? So these are the recovery times for how long it takes for people to get better, okay? Um, so this information right here, you can find this in StatCrunch. So if you go to Canvas, click on Chapter 11 worksheet, click on this link. It'll bring you here. Go down, scroll down to Chapter 11 review, click on the StatCrunch, and here's the numbers here. But if you don't have that, I did drop the link in the chat, but if you don't have these, there's only like 20 numbers here. So entering those is not going to take that long if you just want to enter it in a blank StatCrunch. Okay. Um, Okay, but StatCrunch is going to calculate a lot of this for us. It's going to give us the number for the standard treatment, the mean, the standard deviation. So you don't have to calculate these on your own, okay? We can use method one from page 254. Okay. You do method one for the first one, do method one for the second one, and then I'll give you these numbers and you can fill that in. Okay. Verify the conditions necessary to construct a 95% confidence of the difference in recovery times. So we need to check that it's random. Now, since we have two samples, we need to check that the two samples are independent of each other. And we also need to check that they are independent of the population. And then we need to check that each of them is normal. Okay. All right. Construct a 95% confidence interval. So state the stat crunch path used and the result. So don't just give the result. You don't have to show your work here the way that we did in chapter 10, where you had to show the formula and then substitute in and then show the result. You can just show the result, but the work here is going to be write out what you clicked on in StatCrunch. Okay. So that you'll find on page 262, I believe. That's not it. We're looking for the difference in average between two samples. So here we have tests for the difference between two independent means. Okay. So that is on page 266. Okay. So the StatCrunch steps you're going to click on are going to be stat, tstats, to sample, and then you're either clicking on with data or with summary. Okay. And actually for this case, you can use either one of these. Okay. So make sure you indicate what you clicked on. Okay. All right. Page 565, a simple random sample of US adults embarked on a program of regular aerobic exercise. Their heart rates and beats per minute were measured here before and after with the results at the right. Okay. Verify the requirements needed to construct the confidence interval were met. So we need to make sure that it's random. Okay. So for here, we are not checking if it's independent. We're checking if the two samples are dependent. Okay. I mean, it's not a big deal, but we also need to check to make sure it's independent of the population. Um, so what's the difference here? So in the last one, I have two different types of surgery, right? Um, and we're trying to see which one's better. We have the old standard way that we've been doing things, and this is how long it takes for people to recover after the surgery is over. Okay. And then we have this one with a new treatment that we're trying out, and this is how long it takes people to recover from that one. Okay. So when you're doing this where you have two different samples, okay, and you're going to compare them, there's two ways you can handle that. The first is you have two groups measured once. Okay. That's fine. Okay. Two groups measured once. What you can't have is you have an overlap between the two samples. In other words, you can't have someone in both of these groups. In other words, you can't have someone who does the standard surgery and then they come back in and do the new surgery as well. Because if that person takes a long time to recover, you don't know which one caused that to be a long recovery, okay, or a short recovery, okay. I don't know why you would have the same surgery twice, one in two different ways, but uh, you can't do that when you are comparing two different samples, okay. Now, on the other hand, the other way that you can do two samples and compare them is if you have exactly the same people in both samples. Okay. And that's what's happening here. We are checking people's heart rates before they exercise and right after they exercise. Okay. So in that case, we're looking at two samples that are dependent. In other words, we have one group measured twice. Okay. One group measured twice. Okay. So if we measure, let's see, how many people did we have? We had like 6 people. So we measured those 6 people's heart rates before they exercised and then right after they exercised. What you can't have is you can't have uh, someone in this group where you measure their starting heart rate, but you didn't get their after heart rate. You have to have exactly the same people in both samples, okay? Because let's say that you have someone who's an outlier and you measure their heart rate before the exercise, but then for some reason you weren't able to measure their heart rate after. Like maybe they didn't exercise that day and they didn't give you the results, okay? Or, maybe, something happened with your testing equipment and you couldn't measure their after result, okay? If that happens, you have to throw them out of the sample, okay? And that could cause bias, but what you need is to make sure that you're measuring the same people both before and after. Because if you measure someone just before, they could make your numbers much higher than they should be because they're an outlier, or much lower. And that's fine as long as they're in both groups because it'll kind of even out, okay? Um, but if they're only in one of the groups, then mess things up. So basically, what I'm getting at is when you're measuring two samples, you either need both samples to be completely different, that's independent, or you need to have them be completely the same, which is dependent. Okay. So you can't have a situation where there's some that are the same in both groups and some that are not. Okay. All right. Anyway, that all said, um, we'll come back and we'll talk about all this. Uh, And oh, you got to also check that it's normal, right? Both populations are normal. But again, in this case, you're looking at a single population. So you really only have to check that once. Same with the independent of the population, okay? All right, question 7, page 566. In randomized double-blind clinical trials of a new vaccine, rats were randomized, divided into two groups. Subjects in group 1 received control vaccine, while subjects in group 2 received the new vaccine. Okay, so here we need to make sure that, again, the two groups are completely separate. So there's no rat that's in both samples. You're either in group 1 or group 2, can't be in both. All right. Um, researchers found da, 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 fill in the following information. So remember that X is equal to N times P hat. Okay. And this is going to be on page 264. Page 264 is test for the difference between two independent proportions. Okay. So we're looking at proportions here between the control group and the experimental group. So our hypothesis is going to be that the two proportions are equal. Okay. Null hypothesis is that they're always equal. Okay. And we'll fill in the rest in a second. Okay. So you can write it like that, or you can write it as P control minus P experiment equals 0. Either way is fine. All right, page 567. A researcher for Consumer Reports believes that SUVs have worse gas mileage than sedans. They gather a random sample of both types of vehicles. measure their gas mileage, conduct a test. Here are the results from the StatCrunch for us. Okay, so what type of test is this? So we can tell that looking here. So our null hypothesis is always equal. Okay, the difference between the two, in this case, if we were doing not equal, that's a two-tailed test. This one is less than. So less is on the left. So this is a left-tailed test. Okay. All right. Um, so down here, use the computer output to perform steps 4, 5, and 6 of the hypothesis test at a 5% level of significance. Okay. So step step one, you'll remember, was write out your hypotheses. So we've already got that. Okay. Step two was write out what alpha is. Alpha is this. Okay. And then step three was calculate your t statistic, which is here. So they've done all of that for us. So step four is where you draw your t curve or your normal curve, whichever one you're looking at. In this case, it's a t curve. And then you shade, whether it's on the left or the right. We said this is a left tail test. So you shade the tail over here on the left. Okay. And you calculate what your p-value is. So our test statistic in this case was negative 1.507, right? So that's this right here on the x-axis. But our p-value is this one, 0.0734, right? And then step 5, you compare your p-value to your alpha. And in this case, this one's bigger. So do we reject or not reject the null hypothesis? Do you guys remember? If we have this situation, do we reject or not? Do not reject. Thank you, Andrew. And step 6, you write out there is not sufficient evidence. There's not sufficient evidence to support the claim, and then you write out what the claim is. We didn't actually read what this is. We were just doing the steps here. So we'll come back and we'll fill in what the claim is in a second. Okay. This worksheet does have 6 pages, so it's a little longer than our normal one, but that's okay. Um, company studied 2 programs for compensating its sales staff. 9 random salespeople participated in the study. In the program A, salespeople were paid a higher salary plus a smaller commission for each item they sold for 6 months. In program B, same salespeople were paid a lower salary with a larger commission for the next 6 months. Buying data are the amounts sold in thousands of dollars for each person on each program. So in this case, find the difference between, so the difference, you just go through and you subtract these, okay? So 55 minus 53 is 2, right? 21 minus 24 is negative 3, okay? So some of these are going to be positive, some of these are going to be negative because some people made more money going with program A. Some people might be better at sales, and so they made more with program B. So make sure you're writing down which one's positive, which one's negative as you go through and fill in these differences, okay? This data, by the way, program A, program B, you find that over here in StatCrunch, so it's already filled in here. So I don't think that StatCrunch will allow you to do formulas the way Excel does, where we do equals and then you click on this one, and then you subtract, and then you click on this one, right? That just totally messed up my numbers. So yeah. So you're just going to want to, you could enter these, you could copy and paste these into uh, Excel or Google Sheets and then use a formula that way. But the subtraction here is not that difficult. So there's only 9 of them. So once you've done that subtraction, the above situation is an example of which dependent sampling or independent sampling, and then quantitative or qualitative variables. What do you guys think for 9B? First of all, what type of sampling, and then what type of variable are we measuring here? All right. So Andrew says we're doing quantitative variable, which is correct, because we're measuring how much money people made from the two different programs. Okay. So that's, but we're looking at dependent sampling here. So I'm looking at dependent quantitative. The reason why it's dependent is because the two groups here are the same. So I have 9 people at my company, and I use the same group for both samples. Okay. So in other words, maybe this isn't person one, right? Maybe this is Jack. Okay. And for the first 6 months, Jack made $55,000 selling stuff for me with program A. And then we switched after 6 months. We tried program B, and he made 53,000. So he made $2,000 less. Okay. Um, when you have two different samples that you're measuring and you have two completely separate samples where there's no overlap, you can either be in group A or in group B, but you can't be in both. That's considered independent. Okay. Here we have two groups, program A, program B, but they're the same people. Okay. So maybe Jack is, he's an amazing seller, right? He made $55,000. Person number two, maybe this is John, he sucks. He only made 21,000, right? So the reason this is important is because if you have an outlier like this, where their numbers are very high, you'll see that they're high for both samples, okay? So that's important because really what we're measuring here is the difference, okay? So if Jack was only measured on program A and not on program B, when we calculate the average, because that's what we're going to be looking at, we're going to be looking at the mean, okay? When you calculate the mean, it's going to throw things off, okay? So this is dependent because they're in both, the same people are in both groups, okay? Um, so that matters a little bit as you're writing out, checking to make sure that the we're using the uh, right phrasing when we're checking against the central limit theorem to make sure the requirements are met, right? So on page 265, if you have dependent samples, okay, you have what's called match pairs, okay? So we would write out one group measured twice, okay? But the steps in StatCrunch are slightly different. We do stat, t-stats paired, okay? Now, page 266 is if you have independent means, okay? And it's stat, t-stats, to sample with summary or with data, okay? And here, your independent samples would be two groups measured twice, okay? So that's why it's important that we know which one we're looking at because we're going to click on things a little bit differently in StatCrunch. So here we have match pairs. We're doing page 265. Okay. come back to that and we'll fill in our answers in a second. I'm going to stop the recording and we'll jump back to page 563. Okay.